I'm going to talk about this magnitude 8.8 Russian earthquake that happened off the Kamchatka Peninsula next to the Sea of Ohkotsk, and I'm going to talk about some of the aspects of these very large megathrust earthquakes. I'm also going to talk about the way they generate tsunamis and the way the vagaries of the orientation and the bathymetry, the seafloor, can affect tsunami wave amplitudes. Okay, so let's talk about the earthquake first. So this is the earthquake here, up here, magnitude 8.8. This is very large. There have only been 5 larger than this since 1900, so this is really very large. Okay, there's what's called a megathrust earthquake. It's sitting on the subduction zone where the Pacific plate is subducting underneath the Eurasian plate here. So the Pacific plate is coming up to the northwest like this. It's subducting under this arc here. And as I've discussed before, you have very large areas of interface at these subduction zones. So these are where you can produce very, very large earthquakes. Things like transform faults or normal faults, which are almost vertical, cut through the crust, and they're limited in size because the crust is only a few tens of kilometers thick, the brittle part. So the earthquakes can only rupture surfaces which are only a few tens of kilometers thick. Whereas here, because the oceanic crust is subducting underneath the continental crust, there's a very many hundreds of kilometers of slip surface that can be ruptured. Okay, so that's the first thing. So we get all the really large earthquakes around these subduction zones. And if we look in the history of the region, there's this one here, the magnitude 8.8, 8.7. That happened just the day before yesterday. And all the way down through here, this is Japan here, this is the Kamchatka Peninsula here, North Japan. We can see some very large things. So there's the magnitude 9.1 Tohoku earthquake, 2011 earthquake was there. We've got magnitude 8s all the way up through here. So these are all what will be classified megathrust earthquakes. And in fact, right next to where this one happened, in 1952, there was a magnitude 9 earthquake there. And that probably ruptured a surface something like this. This is the aftershocks, this grey region. This is the aftershocks from this 1952 earthquake. So you can see it's a very seismically active area with very large earthquakes associated with the subduction here. Okay, so this is the USGS catalogue with the last month's worth of earthquakes on it. You can see there is quite a large swarm here, which we will talk about. But in the last month, the previous 2 largest earthquakes before this were these 2 here in Alaska, and this one, which is centered directly on the Kamchatka earthquake. So one of the interesting things here is that there were about 10 days of foreshocks. So this is, again, the USGS catalogue. This is the last month's worth. The ones which are red were in the last hour when I took this screenshot. All of the orange ones are post-shocks, aftershocks from the magnitude 8.8, and this blue one is the magnitude 8.8. And all of the yellow ones and white ones, yellow is the week before and white is the month before. So basically for 10 days there have been a series of foreshocks just here, with the largest being a magnitude 7.3 that I just showed you on the previous diagram. And in fact, this is the rupture surface of the magnitude 7.3 earthquake here. Okay, so is it unusual to see quite such a nice foreshock sequence for these large earthquakes? Well, Earthquake Insights has a very nice blog about this, and they've analysed all of the magnitude 8.5 and above for the last century, and they find that in about half of cases then there are foreshocks. Okay, so about half of these very large earthquakes have foreshocks. So then the question is, well, why can't we then be forecasting them? You know, you've got a nice foreshock sequence, magnitude 7.3, but actually there have been about 16 magnitude 8.5s and above in the last century, but there have been 2,000 magnitude 7s and above in the last century. So actually only in about 1% of time is a magnitude 7 a foreshock to something significantly larger. Okay, so if you're wanting to predict these things, if we're using magnitude 7s as foreshocks, as predictors, we would have 99% of our cases would be false alarms. Okay, so unfortunately, while we do see sometimes nice foreshock sequences, we can't use them as predictors because we don't know whether or not they're going to actually result in something larger. In fact, I was following this magnitude 7.3 because it had itself a few foreshocks and had a nice aftershock sequence, and I was following it to see whether or not I could do something about aftershock decays. So unfortunately, it does seem as though while in half of cases there are foreshocks, we can't use them as predictors because we don't know whether they're going to be foreshocks until after the large things happened. Okay, so if we look at the rupture for this magnitude 8.8, this is the rupture surface. It's really very large. Okay, this is the focal mechanism solution, which is consistent with subduction from the southwest. This represents the movement of the upper plate. This represents the movement of the lower plate. And by inverting the waveforms, the USGS has produced the following model for the rupture surface. So the rupture surface was large. Okay, it was 450 or 500 kilometers across and 100 or so kilometers deep, 150 kilometers deep. Okay, so the colours are the displacement on the slip surface. This is modelled as a thin slip surface. So you got up to 10 meters of slip. Okay, and the contours are the star here is the hypercenter. So that's what that dot is in all of those maps. But actually the surface is much, much larger. So that's where it started, that hypercenter. And these contours are the contours of the position of the rupture surface propagation, so the edge of the rupture in seconds. So in about 3 minutes, the whole of the rupture had propagated. So this took about 3 minutes for all of the slip and the energy to be released. Okay, so it's very, very fast. Okay, so that's the rupture, that's the earthquake. Let's have a think about the tsunamis that are produced. Okay, so here's the hypercenter. This is the rupture surface here, essentially where those aftershocks are. And you can see that essentially we have the Pacific Ocean here. So any waves that are produced are going to propagate outwards down through Japan and across to Hawaii and then the west coast of America. Okay, so how are tsunamis generated? That's the first question. Well, if we think about the Pacific plate here, this is subducting underneath the Eurasian plate in my cartoon. Okay, and if we consider a region which is locked like this, so there's no slip happening, and to produce an earthquake, of course, you have to lock up the slip surface so that the energy gets stored until it suddenly fails. So if we're storing energy at this point here, it's locked up, you're going to elastically deform the overriding and the subducting plate. So the Pacific plate carries on subducting, but there's no movement here, so you deform them like this. This bends upwards, this surface bends downwards as well, and this is all elastic. So when the rupture finally happens, it's going to spring back to its original position. So you get movement here of the seabed. So here in the red, the movement will be down, it's been bent up, and when it relaxes, that's going to fall back down again. And here we get movement up in the black here. This has been bent downwards, and when it finally fails, everything's going to relax back up. So you get movement of the seabed like this. Okay, so that's going to produce a wave, which is something like this. Now remember, this rupture surface was 400 kilometers long and 150 or so kilometers wide. This is a very large wavelength wave. It's going to be tens or hundreds kilometers in wavelength. The amplitude might be quite small. The movement, the total movement on this slip at maximum was 10 meters. Now you're not going to have nearly that much of elastic deformation here of that much, because the movement was along this interface. So this deformation is going to be somewhat smaller than that, tens of centimeters perhaps. So the amplitude of the wave here, the tsunami wave, is only tens of centimeters or so. And if we think about the way that waves decay as a distance from the source, if we had a point source like this, then the amplitude at a particular radius, essentially the energy is radiating over this circumference, and the circumference is proportional to the radius. So the energy decays as 1 over the radius. Okay, so as you go away, if you double the distance away, then the energy is spread over twice the circumference, so it's half as much. Okay, but of course if you have a line source, here's my line source, then as I go away from that line source, this distance, this length of wave here, doesn't increase, so the energy doesn't decay nearly as quickly. Okay, so that's the first point. So here we have the region where there's likely to have been seafloor ground motions, okay, approximately the same as the rupture surface. Okay, so this is essentially a linear feature. Okay, it's not a point source, it's not a round thing like this, it's actually a long, straight long feature. So as the wave goes away this way, it's going to end up, until you get some distance away, it's going to end up seeing this as a linear feature, and so it won't decay in the same way as if it was a circular feature, okay, at least in the near field. So if we consider what that's going to do to the decay of the waves, this is a simulation from these people here in this paper, okay, for Japan rather than for Kamchatka, but this is if there was an earthquake which was essentially a circular source, a point source, and the brightness of the colours are the amplitude of the wave, okay, centimeters. Okay, so you can see that it decays pretty much as parts of a circle as you go around there. But this is on the right, this is treated as if it was a linear feature, okay, with an aspect ratio of 9:1. Okay, what you see is that in the direction perpendicular to that linear feature, you get a much longer region of high amplitude. It's still 10 centimeters here, at 2,000 kilometers away from the source. Okay, so you get much more directivity if you get these linear features. So if we think about the Kamchatka earthquake, here's that surface. You should see directivity like this. It's pretty much pointing towards Hawaii. Okay, so this is why there were quite significant tsunami warnings, particularly for Hawaii. Okay, but the other thing that you see is that it's not just a simple straight line. There's all of this complexity. Here you see it in particular, these kind of little rays, some of which are stronger, some of which are weaker. And this is related to the shape of the seafloor, the bathymetry. Okay, because these waves are such long wavelength, tens or 100 kilometers wavelength, that means they're sensitive to the seafloor. Okay, and so the topography of the seafloor changes the way that these waves propagate. We can see that if we look, in fact, at the times, the predicted times for the tsunami arrivals. So this is from NOAA, the National Oceanic and Atmospheric Administration in the USA, and this is actually the tsunami times for the Kamchatka earthquake. So these contours are 1 hour contours. Okay, so it's moving at several hundred kilometers an hour. So this is a 5 hour contour. Okay, there's Hawaii just there. Okay, and what we see, if we look in, say, these regions here, north of Kamchatka, or actually this region here, in the Ohkotsk Sea, or down here, this is quite shallow water here, and this is very shallow water here. What you can see is that the contours are much closer together. And again here, as you get onto the continental shelf here, on the edge of Alaska, you can see the contours are much closer together than in the open ocean. And that's because as the water depth gets shallower, then the speed of the wave velocity, goes down. Okay, so it's a refraction process. Okay, so the wave velocities go down. Okay, and so you can see it's really nice if you look at these wave fronts here. They come along. Once you go across the trench and onto the overriding plate, the wave gets bent around like this. Okay, and because the wave gets bent around like this, essentially this then propagates in a different direction. So by changing the wave speed, you can focus waves and you can defocus waves. So if we think of this at the shallow shore, then what we have is a wave coming like this. Here's a nice linear wave coming in like this. We have regions which are shallow here, deep here, and shallow here. So the wave is slower in the shallow regions, so the wave front gets bent, okay, like this. And so you see these waves which are bending round in the bay. But the other thing that happens, of course, is that the front of the wave hits the shallower region before the back of the wave. So the back of the wave starts to catch up with the front of the wave. And in fact, this is what produces breakers. This is basically the wave piling up on itself as it gets into shallower regions. So this is why when you get out into these big things, they may only be 10 centimeters of displacement of water at the source. When they get into shallower regions, they start to pile up on each other, and you produce massive breakers, and these are what the big tsunamis are. Okay, but of course, all of that then depends on the vagaries of how the wave is slowed down. So it depends on the source position and directivity. Okay, it depends on the bathymetry at the source as well, which then defines how this wave is going to propagate outwards and how its amplitude is going to maintain. And then it also depends on the bathymetry of the coastline as well. So in this particular case, we've been very lucky, although it's been a very large earthquake, we've been very lucky that the directivity didn't point directly towards Hawaii, and also the source and coastline bathymetries happen to have worked together to mean that there hasn't been a really destructive tsunami. And that's just luck, really. That's luck that the seafloor here at the source and the seafloor along these coasts have interacted in a certain way with the source as well, to avoid there being a really, really large tsunami. And that's really everything I wanted to say. Just to say that these are very useful resources. The USGS Earthquake Catalogue and Earthquake Insights as well has some very good insights into the larger events as well. Thank you for listening.